part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss boundary conditions and magnetostatics. And then after that, I'll do a wrap-up of everything that we've talked about so far regarding magnetic fields. Let me first begin with two equations that characterize behavior of magnetic fields. First equation is that the magnetic field is divergence-free. As it turns out, this holds not only in static situations, but also holds for time-varying fields as well. Notice this is in contrast to the divergence of the electric field. Divergence of the electric field was proportional to the volume charge density. Here, this is zero because it's an experimental fact that no magnetic monopole has ever been observed. Two other equations. The curl of the magnetic field is proportional to the volume current density, and its counterpart in electric fields, electrostatic fields, the curl of the electric field is equal to zero. Let me look at this expression in a little bit more detail. I'm going to apply this to a closed, or to a volume. I can make use of the divergence theorem, and that just tells me that the flux of the magnetic field through a closed surface vanishes. So let's consider a particular example. Let's suppose that we've got a current sheet. And I'll construct a pillbox. And I'll assume that there's a surface current density. What this expression tells me is that the normal component of the magnetic field is continuous across this boundary. We have written symbolically, magnetic field above the normal component is equal to the magnetic field below the normal component. So this is in contrast to the electric field situation where if you had a surface charge density, there in fact was a discontinuity in the normal component. Here, of course, the normal component is continuous. Well, let's construct an Amperian loop now. You notice I'm taking my Amperian loop. There are two ways you can do it. You can orient it such that it's perpendicular to the surface current density, or you can orient it parallel to it. And in this case, I'll make use of Ampere's law in differential form. You take the integral of the magnetic field around this closed path, and what you'll see is that there is in fact a discontinuity in the tangential or parallel component of the magnetic field in the presence of an interface. So this holds if I have drawn my loop such that it's perpendicular to the current, but let's suppose I took my loop such that it was parallel to the current, what you'd find is that the component of the magnetic field parallel to surface and to current is continuous. I've got 3 observations regarding the behavior of the magnetic field across an interface that carries the surface current density. And those 3 statements can be expressed in one simple equation. And that is that there is a discontinuity in the magnetic field across the interface, and that is equal to mu naught times the surface current density crossed into the normal component to the surface. Now, one thing I want to point out, and we clarify this, we did a problem using Ampere's law where you had an infinite surface or infinite current sheet, and you had a uniform surface current density. And in that case, we reckoned that the magnetic field vanishes, the normal component of the magnetic field vanishes, okay? So you're looking at that, if you're thinking about that case in the back of your mind, you're looking at this, you say, wait a second, aren't we contradicting ourselves? I mean, why are we even bothering here? This is one of the things about electromagnetism. You've got to be very careful about what problem you're addressing. I said nothing about this being an infinite current sheet, and I didn't even say anything about the current surface current density being uniform. I'm simply applying the fact that the magnetic field, the divergence of the magnetic field vanishes to this situation to derive a boundary condition, and then also applying Ampere's law, both perpendicular to the surface current density and also parallel to it, to derive several other observations regarding magnetic field boundary conditions, and then of course all combining those 3 into this one expression, okay? So just bear in mind, it's not the same problem, even though it looks like it, to what we discussed before. In that case, when we use Ampere's law, again, remember it was for an infinite current sheet, and it bore in uniform surface current density. Here, this is just some surface. I've said nothing about how big it is, and also we have said nothing about whether it's uniform or not. So I just want to clarify that point, again, just to be put a fine point on the difference between what we're talking about here and then that problem that we worked out a few lectures earlier, okay? Okay, so that is your discontinuity in the magnetic field. What about magnetic vector potential? We took the divergence of the magnetic vector potential to vanish. So therefore, using the same kind of reasoning, I can say, well, the normal component of the magnetic vector potential across the interface must also be continuous. Now, what about the tangential component? The curl of the magnetic vector potential is equal to the magnetic field. So I'm going to apply, basically take the dot product of both sides and then integrate over some surface. And note that the surface is not closed, okay? But I can make use of Stokes' theorem to convert this surface integral on the left-hand side to a line integral. Now we're taking the line integral of the magnetic vector potential around a closed path and the closed path that encircles this surface, or bounds this surface, okay? Well, it's not automatically true that this is going to vanish. Generally speaking, or I should say for an open surface, if you will, this is not going to vanish. It's only for a closed surface that the flux through that flux of the magnetic field through that closed surface vanishes. This doesn't. However, I can take the Amperian loop as narrow as I like. If I do that, I can make this area smaller and smaller. So therefore, for a very narrow loop, the flux is going to go to 0. And therefore, the tangential component of the magnetic vector potential is going to be continuous as well. So summing those two observations up, I wind up with the magnetic vector potential is continuous across a boundary or an interface. Now, what about its derivative? Well, as it turns out, the first derivative inherits the discontinuity in the magnetic field. So we wind up with the partial derivative of the magnetic field vector potential above minus the partial derivative of the magnetic vector potential below is proportional to minus the surface current density. Okay? And those are your boundary conditions. And if you like, you can play around with them, look at some of the problems we worked through. So let's talk about some of the problems we worked through so far. Let me just leave this up on the board for one more minute, a few more minutes, an instant, and then we'll press on. Looked at the Lorentz Force Law, and we investigated three basic types of motion. Number one, cyclotron. Basically, the charged particle just gyrates about some guiding center and is at rest. A helix, where the particle gyrates about some center axis, basically, but it has a velocity component that causes it to travel in a spiral. And cycloid, that's if you have a uniform magnetic field and also a uniform electric field in addition to that. So we went through the math there, and I do have simulations of those three types of trajectories posted online. You can find the link to that at the BocaPhysics website. And I also pointed out, when we were talking about this, that this isn't just the kind of motion you can have. Like, it's far more complicated. If you're into plasma physics, for instance, you'll be investigating the trajectories of particles in the presence of non-uniform magnetic fields and non-uniform electric fields as well. But we just stick with uniform fields in electromagnetism. Okay, we next moved on to the Biot-Savart law. Similar expressions for a surface current density and also for a infinite wire. Okay, so we applied this to several kinds of problems. We looked at a wire segment, an infinite wire, and then we also looked at the magnetic field due to a circular loop and on axis. first we were just calculating the magnetic field due to a circular loop on its axis, not generally speaking, not at a general point in space. We applied that result to Helmholtz coils. And a solenoid. Now moving on, we derived Ampere's law. Applied this at the fact that the line integral of the magnetic field around a closed path was proportional to the amount of current enclosed by that path. So we looked at infinite wires, to the thin wire surface current density, rather uniform surface current density, and a uniform volume current density. And what we saw in each of those cases that outside the wire, magnetic field had exactly the same form, U dot I over 2 pi s in a circumferential direction. So, this is a big difference between how electric fields and magnetic fields behave. Electric fields, students are instructed that they originate on positive charges, terminate on negative charges to go off to infinity. Magnetic field lines, they're instructed form closed circular loops or closed loops or go off to infinity. But when you look at these problems that we do in undergraduate electromagnetics, you might get the impression that magnetic field lines form closed loops, simple closed loops. In fact, if you look at some of the simulations of systems that are really not all that complicated, what you'll see is surprisingly complicated magnetic field structures. So bear in mind that when you read something like forms a simple closed loop or goes off to infinity, that things get a lot more complicated really fast, even if you don't have all that, say, complicated a system. If you go onto my website, BocaPhysics.com, I do have links to magnetic field line simulations. And what you'll see is those standard textbook problems. You'll see the magnetic field loops, nice simple loops that lie in a single plane. And then at the end, I include 3 simulations where the magnetic fields have a more complicated structure. And the systems in question are not really complicated at all. You just have 2 infinite wires perpendicular to each other and a magnetic field superimposed upon that. And what you'll see is really, really interesting behavior. And then I have one simulation where I have the magnetic field due to an infinite straight wire that lies along the axis of a current carrying ring. And there's also a uniform magnetic field superimposed on that. And again, you'll see complicated structure. In fact, fusion researchers classify relevant types of surfaces. You have rational magnetic field lines that close after a finite number of loops. You have ergodic, in which case the magnetic field lines lie on the surface. They basically cover the whole surface. And stochastic, in which case you have magnetic field lines that fill the volume of space. So I just want you to keep that in mind as you're doing these problems and learning this material. Okay, so that's infinite wires. We also looked at infinite current sheets. Looked at 2 kinds of problems. You had uniform surface current density, which I was just talking about a few minutes earlier, and also an uniform volume current density as well. And what you saw in those cases is that, let's suppose that the current was flowing out of the board. You can just use the right-hand rule. The current then would flow to the left above the current sheet, and actually it's left and then to the right, okay, below it. And what you also saw is that outside the surface, the magnetic field was uniform in magnitude. So that's analogous to the situation where we dealt with infinite charge sheets, where the electric field was uniform above and below. However, in that case, electric field pointed away from it if it was a positive charge, towards it if it's a negative charge. Here, the magnetic field is actually parallel to the surface, okay? Parallel to the surface, but perpendicular to the current. And we also looked at the problem of a solenoid and a toroid. Introduce the magnetic vector potential. And again, similar forms for if you have a surface current density or a line or just a wire. As I pointed out in that lecture, you cannot use this expression if you've got an infinite current distribution. So that's analogous, again, to the situation in electrostatics. If you had an infinite line charge, an infinite current sheet, you couldn't apply the counterparts, the electrical counterparts to these. And the reason why is because this is going to blow up. So you have to resort to a different technique, which we did. And we calculated the magnetic vector potential due to an infinite wire. And then we also looked at magnetic vector potential due to a solenoid. Only in this case, we looked at it at everywhere, not just, oops, and I'm getting ahead of myself here. We looked at a current loop. And there it wasn't just limited to a just the z-axis, but it was everywhere. And then we also looked at a spinning sphere with uniform surface charge. This one's not too much effort to work out. This one is more challenging because you've got to resort to elliptic integrals. And this is the kind of problem you usually don't encounter in undergraduate electromagnetism. Usually that's graduate EM. The reason why I introduced it now is because it seems like a lot of students don't actually get to elliptic integrals in their math physics classes. So once you get to graduate school, you'll have a few problems involving elliptic integrals, and you should be familiar with them. And also, for my part, I've always found it annoying that you're really limited in the kinds of problems you can work out. So a lot of times you'll just stick to just axis of symmetry, but here they analyzed it everywhere, arbitrary point in space, okay? And this last one, spinning sphere with a uniform surface charge, we also discussed as well. Okay, and we also looked at some more magnetic field problems. And here we looked at a current loop, starting from the magnetic vector potential. And we also looked at a solenoid, and there we calculated the solenoid, field of the solenoid everywhere, not just on an axis of symmetry. And if you compare this with this, or even this, you can see that this is far more complicated to arrive at an answer. Ampere's law by far gives the easiest way of calculating the magnetic field due to a solenoid. Even over here, this is not quite as complicated a problem, but again, it's just we did on the axis of symmetry there and approximating the solenoid by a stack of circular loops. Okay, and let's see, current loop solenoid, and we did one more kind of problem, and that was Another problem with a spinning sphere. Here we did an expansion. Again, it was analogous to the analysis that we did in electrostatics. We looked at dipoles. We looked at a current loop, a spinning sphere, and a spinning cylinder. And you know, when you're being given homework problems or tests, you know, it might be one of these fundamental types of problems, or it might be a case where you have to make use of the superposition principle of magnetic fields. That's usually found the case when you know, you want to use Ampere's law. You might have a long wire that has a tube, a hollowed out tube inside of it, and you want to figure out, well, what's the magnetic field at a certain point. Well, you make use of Ampere's law and making use of the superposition principle, and then you can arrive at an answer without too much effort. Okay, so that's where we stand so far. We are rapidly reaching the end of this first semester of electromagnetism. We do have one more field to cover, and that is with magnetic materials, and I will be getting to that next.